All right, good morning. How is everyone? How was your weekend? Crickets. All right, well, hopefully my microphone works. So we lucked out on Friday. We had sound to go with our video, and I don't know how that happened because the sound failed in the morning class partway through, and it failed. It worked in 222B, and then it failed for 215. So I don't know what happened, but hopefully people can hear me. All right, so oh good, someone can hear me. Cool. So we are going to talk about the midterm presently. So the midterm will be on Friday. Okay, it will be. Thank you for the confirmation. Midterm will be on Friday. It will be at 11 o'clock. It will go until 11:55. It will show up in it's on Canvas right now. It will unlock at 11, and it will look like a homework assignment, right? It'll be a PDF file that you can look at on Canvas or you can download. You're going to write up your answers in your favorite editor, save them as a single PDF file, and upload that PDF to Canvas. Okay, it's not a fillable PDF. The PDF that you're going to see on Canvas is just a list of questions, and then you need to actually create a PDF document with your answers and upload that to Canvas. If you've taken 215 with me online, if you're taking it now, you know how to do this. This is how you do your homework, right? Except I want you to type up your answers instead of scanning a picture. If you don't know how to do this, figure it out before Friday. Okay, if you're not absolutely sure you know how to make a PDF out of your typed up answers, figure it out ahead of time. If you don't know how to figure it out, right, come by office hours and we'll go through it. You can share your screen and we'll go through the steps and make sure you can do this. Okay, what you do not want to have happen is, you know, you go into VI and you write your code and you're all ready to submit, and it's 11:48 and you've got 2 minutes left, and you don't know how to create a PDF file, right? So make sure that you're comfortable with the mechanics of how you're going to make a PDF. Just like you would a lab report, right? You've done 120, 250, maybe 270, right? So just like a lab report. And I don't care about, you know, formatting or anything like that. I just want to see, you know, the question number and your answer. Question number and your answer. Okay, so very straightforward. So the exam will unlock at 11 o'clock on Friday. And I'm giving you 55 minutes, okay? I want you to be on Zoom during that time, which is great for the 14 people who are here, but not for the others who aren't. But I want you to be on Zoom so that if there are corrections, typos, clarifications, things like that, I can put them in chat, or, you know, if it's really dire, I can, you know, use my microphone, but I can let you know about it. If you're not on Zoom, then there's no way for me to, like, you know, tell you, hey, you know, question 3 is impossible the way it's written, so do this other thing instead. I'll also send you a reminder when it's 11:50 and you have 5 minutes left. The exam will not automatically close you out at 11:55. So if you don't get it turned in on time, turn it in as soon as you can, but it's going to penalize you 5 points per minute. Okay? So, and this is according to Canvas's notion of was it turned in on time or late. So if Canvas says it was turned in 5 minutes late, you're down 25 points. Okay? So you really got to take responsibility for turning this in on time. Right? Don't play with the deadline. I would say treat it as a 50-minute exam. Turn it in by 11:50, and that leaves you a few minutes. Oh, my internet went out. I had to reboot my machine. That kind of thing. 5 points a minute while that's happening. Okay, so don't mess with it. All right, let's see. So turn it on time, be on Canvas. So this was all stuff that I posted in an announcement last night. The other thing I mentioned was that tomorrow's office hours will start at 9 o'clock instead of 8:45. I have a CS meeting from 8 to 9, so I'll be coming into my office 15 minutes late. The other aspect of the exam is there will be an honor statement at the top of the exam. And you need to review this honor statement, and then at the top of your answer sheet, write the words honor statement and then type your full name next to it to indicate that you agree with the honor statement and you agree to adhere to it. So the gist of the honor statement is basically you're going to work on the exam alone. All the work you turn in is going to be yours and yours alone. You're not going to give help to anybody else. You're not going to seek help from anybody else except for from me. Okay, if you have questions, you can send me a message in chat, and you know, I'll help you if I can. But nobody else can help you. You can't go online. You can't use online resources, things like that. You can use your textbook. You can use your old code. You can use your notes, but no Googling, no chegging, things like that. The other thing is, I don't want you to use any compilers. I don't want you to use any syntax checking or syntax completing editors. Okay, no compilation, right. If you use a syntax highlighting editor, that's okay. I'm not going to make you turn that off. So if you use VI and you have color highlighting turned on for syntax, I'll let you do that, okay? So the VI server is okay. The VI on the server is okay. But don't GCC it. Don't use, you know, IntelliJ or Eclipse or Visual Studio or anything else that's gonna, you know, type in, you know, pieces of your code for you or tell you that you're missing something here or things like that. So yeah, disable some plugins if you got them. All right. Any questions about those logistical aspects? All right. So what are the items that may be on the exam? Basically anything we've done up through Friday, so I will not have questions on trees, but anything on structures, mallocs, allocating space, linked lists, sentinel nodes, doubly linked lists, circular linked lists, stacks, queues, hashes, probing, chaining, hash functions, everything we've been talking about. Anything we've done ODPs on, anything from the programming assignments, anything we've ever talked about in lecture is fair game. But I'm going to stick with the highlights, right? So you're going to see some programming questions that will involve working with structures, allocating memory, playing with linked lists. You may have some questions that require you to write an entire C program. There may be some cases where you're writing a function. There may be some cases where you're just writing a few lines of code. And make sure you understand what the question is asking you to do, so that if I'm asking you to write 3 lines of code, you don't, you know, do include standard IO and integer main argc argv and all this stuff, right? Or if I'm asking you for a complete program, you don't just write, you know, a 5-line function. So make sure you're answering the question that's asked. So there'll be 2 parts to the exam. One part will be programming questions, and then the other part will be some short answer, fill in the blank, multiple choice conceptual things. Good fodder for conceptual questions: GDB, makefiles, valgrind, stacks, queues, hashes, linked list, conceptual ideas like that. Hey, welcome to class. All right, I'm hoping it's doable in like 50 minutes. But definitely turn it in by 55. Would it be possible to post an example exam just so we can see the format? Not like any actual CS questions, but just so I can figure out the best way to make my PDF quickly. Kind of like how you posted your practice exams. You could practice the formatting in Canvas last semester. I mean, the exam's going to ask you to write some code, or, you know, multiple choice question 3 is Hello Kitty, this, or this, A, B, C, or D. And just type up your answers like you were doing a lab report, right? So make a document, put your name on the top, type the number 1, type in your code. Type the number 2, type in your code. Type the number 3 and type the letter C if that's the answer. Type the number 4 and, say segfault if that's the answer. I'm not worried at all about syntax or anything like that. So similar to 224, except you're not uploading into Canvas, right? You're making a PDF and uploading that PDF. So 224 and previous 215s, this was done through a Canvas quiz, and there was a area next to each question on Canvas that you would type your answer into. I'm not doing that, okay? That has been filled with difficulties of various types. So I'm trying to get as close to the experience of handing you an exam and having you write down answers and turn in your answers. I'm trying to kind of mimic that. So yeah, type it up in Word and export it as a PDF. That would work great. If you want to type it up in VI, when you're done, just copy and paste it into Word, right? But again, do that before Friday if you've never done that, right? And if you've never done that, it's something you want to figure out how to do, because you're going to be writing reports and papers, probably all your life, certainly all your time in school. And if you ever want to put code into a report, well, you got to know how to copy and paste from Word into VI, or from VI into Word, and so on. But you can use Word, you can use OpenOffice. If you know how to use Google Docs and export as a PDF, you can do that. All right, other questions about that? Can Kate convert into a PDF? I don't think so. I don't think it'll do PDFs. But, do that and bring up your favorite writer program. Copy it, paste it in there, and then just, do the export as a PDF. Or there's yeah, that's a good question. So on my system, at least, I can print, and I can select a print to PDF. So that's another possibility. So that works for pretty much everything. If you're really good, you write a daemon, so you can just LPR your file on Unix, and instead of going to a printer, it takes the PostScript and runs it off into a PDF. That's another option. All right, we're taking 220, 215 on the same day. I'm anxious about that. Yeah, that's a lot, and I debated that when I set up the schedule, but I kind of need the extra day on Monday to get all the stuff graded, because you also have PA3 coming in that day, and so it's one big pain point for everybody. Oh, and physics on the same day, that would be harsh. Yeah, so practice for final week maybe. But I think the exam in here will be pretty straightforward. If you've been doing the ODPs, if you're up to speed on the programming assignments, And if you refamiliarize yourself with the other stuff that we've been doing, I think you'll be okay on the final. It should allow multiple submits if you want to save your state as you're going. If it doesn't, I will change that, but let me eyeball right now. People like physics, huh? Let's see, what have I got? File uploads, allowed attempts, unlimited. Yes, so you can do unlimited submissions. So you can get halfway through it and submit, and then make a little more progress and submit, and you can keep doing that. But I'll grade the last one that you submit. All right. Any other questions on kind of logistics, mechanics of the midterm, which we've actually been talking about for the past 16 minutes? All right. Cool. Let's see. Come by office hours if you're finding the programming assignment. If you're running into issues with that, come by office hours and we can work on the specifics. Just remember, tomorrow my office hours start late. But yeah, we can definitely go over it and make it manageable. So to confirm, it has to be typed and in a PDF format. That is correct. I don't have any particular requirements how you lay it out, as long as I can see which problem you're answering and I can see your answer. So when you get to the multiple choice section, don't just say A, B, B, A, C, D. Put the number of the question next to it, just so you don't get out of sync by one or something like that. But I'm not worried about format or headings or titles or anything like that. Put your name on it just for the heck of it, but you're going to put your name in the honor statement anyway. All right. So a couple of things that came up in email over the weekend, and that I worked with some people in office hours with also. So suppose we malloc space for a say a linked list, but it could be for anything, and let's suppose that somewhere in my code I do something like this: struct node temp, and I set temp equal to list. And then somewhere in my code, I'm ready to exit and I want to free my list. You do not need to also free temp. Okay? You're not freeing things because they're declared as a struct node star. You're freeing things because they point to something that was malloc. And what you're freeing is that thing which was malloc. So here's the action that's happening. Right, when we say struct node star list equals malloc, we're creating a block of memory, and list is pointing to that. And down here, when I say temp is a pointer to a node, temp is some variable, but it doesn't point anywhere in particular. But when I do this, temp equals list, I'm not making a copy of this node. I'm saying temp points to this node. And so when I say free list, that gets rid of that block of memory. And if instead I had said free temp, it would have gotten rid of that block of memory. I could do either. But if I free list and now I try to free temp, the system's going to say, okay, let's get rid of the block of memory temp points to, and it's going to look and say, it's not pointing to a block of memory. Ah, it's going to throw its arms in the air and it's going to run around and scream. And that's when you get all that output from valgrind. Right? So the free statement is not, doing something with these variables, it's doing something with what they point to. So I could have 100 variables pointing to this block, right? And if I free any one of them, that block goes back into the memory pool and we're good to go. Let's see, I know it's not as good as what it does, but I sometimes wonder if a program could disregard code that doesn't work and keep moving on. Yeah, that would be cool. And I think that's a cool idea. I seriously have this idea for like an emotion-driven computer that would do things like that when errors happened. Instead of just exiting, its mood would go down, And if its mood dropped too far down, then it would start doing things incorrectly, or start, doing extra things like disturbing other variables or things like that. But seeing what we could get out of that. Yeah, someone says they spend more time on one valgrind error than they did on the entire thing. That can definitely happen. The good thing is that once you've chased down a few of those valgrind errors, you'll be really good at avoiding them. And if you do introduce one, finding it pretty quickly. And don't underestimate adding debugging symbols before you run valgrind, because that'll help. And when you're happy, it could try to anticipate what you want to do and run it before it actually gets to that part of code. Yeah, that would be sweet. And I'm not convinced it would work worse than like a lot of unnamed systems that we use today. One question, is or should we put head and tail in the structure as opposed to a node defined outside the structure? I did the latter, but wondering if in a queue it works inside the structure. So the head and tail of a queue, so queue is implemented as linked lists, right? The head and tail are already well defined. Right, so head and tail. But if you want variables pointing to those, you can set those up where you like, in your main program, for example, or something like that. But if you're looking for a way to quickly get to the tail without traveling through the head, that really needs to be part of the queue. And if I make it just kind of a variable in my main program or something like that, I'm kind of breaking the notion of an abstract queue. Because now I have this like global variable typically, right? And what if I want 5 queues, right? Each one needs to have its own tail pointer. So at that point I would probably, make this a part of the node structure and just use it, in the Sentinel node or something like that. But there's different ways to do it, and when we get to Java, all of that becomes, much clearer. Is it bad to use the same structure for both stack and queue, then not use all the fields for the stack? That's fine. That's totally fine. So have like a node that includes like a tail pointer maybe, and use that for the stack. I'm okay with that. And yeah, there's a good chance you'll reuse a lot of your code. You can probably reuse the initialize and the print and write custom add and remove functions for the stack and the queue. Sentinel and null, I'm not sure what the question is in response to. It was probably something I said a minute ago. Yeah.
So you said that they were well defined, and I was wondering if they're Sentinel and null, or if the head and tail are different. And I know you've probably gone over this before.
The head is always the thing the Sentinel points to, And the tail is always the last node in the linked list. So even if I don't have, something that points to the head and the tail, if I have a linked list that's implementing a queue, and let's say my sentinel is called Q, then Q arrow next, that's always the head. And when I want to insert, I insert right before that. Or when I want to remove, I remove, that first node. When I want to find the tail, I can do it by just traveling down the list until I'm at a node that doesn't point to anything except null. That's the tail. And when I want to add something, I make a new node and I point that tail to the new node. So yeah, tail's last node that isn't null. All right, and just to mention one other question that came up in email, this business of malloc. It seems like we can assign the result of this to a number of different things as long as it's a pointer. It could be a pointer to an int, or a struct node, or a struct t node, or a q node, or whatever. And malloc is declared, I believe, to be a pointer to a void. A void, not a pointer to a void or watch out for, but a pointer to type void. And I think the compiler takes that as saying, hey, as long as you assign it to a pointer, I'm happy. But sometimes you'll see, equals something like this, where we're casting the pointer. So in C, if you put a type in parentheses before an expression, you're asking the compiler to convert this thing to that type of variable. So if you have a float and you want to convert it to an int, right, you can try to do something like that. And that int in parentheses says I'm trying to change this from a float to an int. I don't think it actually works in that direction, but that's where you'll see this sometimes in using malloc statements. You're casting it to tell the compiler, hey, this thing's actually a pointer to a struct node. The truth is, it doesn't matter, because a pointer is a pointer is a pointer, right? It takes the same amount of stuff and it gets managed in the same way. So we don't see this much anymore. All right, any other questions, concerns, comments? All right, so back to binary search trees. So we went through the basics of trees on Friday, and we really kind of laid the foundation for the next couple of weeks of material. So let me show you an example BST. Right, so there's a randomly drawn tree, and it's a binary search tree in particular because it has this property, which is that for any node that we look at, everything to the right of that node is bigger and everything to the left of that node is smaller. And by right and left, I mean, what's to the right of 100, all of this stuff. Even though this comes off to the left, basically if I go down to the right, I see another tree. Everything in this tree has to be bigger than 100. And if I go to the left, I see another tree here. Everything in this tree has to be less than 100. And that property has to be true for both of those trees. So this tree down here, everything to the right of this node has to be bigger than 200. And at this point, everything to the left of this has to be smaller, and everything to the right has to be bigger than 400. And this has to be true everywhere in the tree. There's a 900, everything over here has to be smaller than 900. Here's a 20, everything over here has to be bigger than 20. Here's a 40, everything here has to be bigger than 40. Here's a 45, everything left there has to be less than 45. So yes, exactly. You can search for a number by taking advantage of this property. So let's say you want to find the number 300. Our trick was compare it to the root. 300 is bigger, so it must be to the right. Compare it to the root. 300 is bigger than 200, so it must be to the right of this. Compare it to the root. 300 is smaller than the root, so it must be to the left. Compare it to the root. Hey, there's our number. 300's in the tree. If you're searching for the number 250, it's got to be bigger than 100, it's got to be bigger than 200, it's got to be smaller than 400, it's got to be smaller than 300. Oh, there's nothing to the left of 300. That must not be in the tree. So we can write a pretty straightforward search algorithm. And it would look something like this. Well, let's make a structure. So let me call this a T node. And let's suppose we're storing integers. So I'll have a field called data. And I'm going to have pointers to other nodes that I'm going to call left and right. So nothing about trees will be on the test, on the midterm. All right, so this is a working tree node. It's got data, it's got pointers to the left and the right. And if there's no child to the left or the right, then these pointers are equal to null. So similar idea to a linked list. So here's our binary search tree. Let's imagine a search algorithm. Which searches starting from a root for a number. The root is the thing that we have that gets us to the tree. Right? It's a pointer to this node, and that's the only thing we have that gives us access to the tree. But it's the only thing we need. If we can get to this node 100, we can get to any of these other nodes. We might have to work to do it, but you know, I can get to this 41. How? By going left, left, right, right, left, left. And that's the only thing from which that is true. If I start with, you know, a pointer to this 200, I can get to all of these nodes, but there's no way I can get back to the 100 or to anything over here. So the root really is the thing that gives you access to the entire tree. So that's typically where we're going to pass to our functions, is a pointer to the root. And so this is going to search for this number in this tree. So what am I going to do? Well, I'm going to set a temp equal to the root. And I'm going to do the following. If temp arrow data equals the num, I'm going to return success. Because I found my number. Let's see, by definition, a BST has no parent node. Well, you know, technically, this thing right here is a binary search tree. And that whole tree itself is the child of this, the right child of this node 200. So yeah, a binary search tree could have a parent. But there's no way to get back, unless you have pointers going back up, which we'll do sometimes. But for now, we're not going to. Yeah, you're welcome. All right, so if the root of the tree matches our number, we're done, right? Hey Nick, here's a tree. Can you tell me if 100's in there? Yeah, it's in there. Okay, that's a good job to have. All right, but it's usually not that easy. Usually we're not looking for the thing that happens to be at the root. So now we have a couple of possibilities. Suppose the root node's data is bigger than the num. So let's say we're searching for 20. Okay, if the root's data is bigger than the number we're looking for, what do we want to do? We want to move down to the left. So we're going to say temp equals temp left. And we're going to go back up to the top. Cool. All right, on the other hand, we don't really need an if because there's no other possibility, but if the root node's data is less than the number we're searching for, so we're searching for 250 and the root node is only 100, so it's smaller, we want to move down to the right subtree. So we're going to change temp equal to temp right, and we're going to go back up again. So this is our basic, moving down through the tree. We start at the root. If that matches our number, fine. Otherwise, we're looking for a 20. Okay, let's change temp to be right here. And we're looking for a 20, and that's smaller than 50, so let's change temp to be right here. And now temp data, right, the root of this tree, matches the number we're looking for. Success. We found the number. All right, good so far on this. We've got to finish this up though, but so far so good. So here's the question. What happens if what we're looking for is not in the tree? If the number's not in the tree, something's going to end up being equal to null. Right, so suppose I'm searching for 1,000. So I'm going to start off with temp equal to here. 1,000 is bigger than that, so I'm going to change temp to be here. 1,000 is bigger than that, so I'll change temp to be this. 1,000 is bigger than that. So I'll set, temp equal to temp right and go back up here. Well, temp data is less than the number we're looking for. If I execute this statement once more and set temp equal to temp right, temp is going to end up null. And now when I come up and I look at temp arrow data, I get a seg fault. So when I move down to the point where temp is null, that's where I know I didn't find my number. So I can add one more check in here. So let's see if our node's not found. So the root node's bigger than our number should be to the left. So here I can say if temp left is null, then I can say not found. If it's not null, I'll change temp to that left subtree's root. I'll go back and I'll try again. And same thing down here. If my number is bigger than the root, I should move to the right, but first, let's see if there is something to the right. So if temp right equals null, then we can say not found. All right, making some sense? Binary tree code is really pretty. It won't feel like it when you're writing it, but when you've got it working, you just kind of look back at it and it makes you smile. Especially once we start doing it recursively, which we'll get to later in the week. It's got an elegance to it that is unlike most other structures we've worked with. All right, so what about inserting? Yeah, so this has to go in some kind of while loop. You could do this as a while forever loop. That's probably the easiest way. Or, you know, you could make a termination flag and say, while we're not ready to terminate, keep doing this, and then here you could set your termination. Usually just a while one flag, while one loop works well to do this going back to the beginning. All right, so let's add something to our tree. Somebody give me a number. Give me your favorite number that's not in the tree already. $88, good. So let's put an 88 in the tree. So where should the 88 go in order to maintain the properties that this needs to have to be a binary search tree? Remember that main property is everything to the left of a node has to be smaller, everything to the right has to be bigger. So where would an 88 go? To the right of 50. Definitely to the left of the root, so somewhere in this tree. And it's got to go to the right of 50 because 88 is bigger than 50. So it's got no choice. It's got to go right here. That's where I did pencil. And that's the only place it can go. It can't go over here because it would have to be smaller than 20. It can't go over here, or here, or here, or here, or here, or here, because it also has to be less than 50 if it's anywhere over here. And it can't go anywhere on this side because these things all have to be bigger than 100. So it's forced to go exactly one place, and that's right here, to the right of 50. Now how do we find that algorithmically? Same way that we search. If we were searching for an 88, we'd start here and say it's got to be to the left. We'd find the 50 and say it's got to be to the right. And we would see that, you know, there was nothing to the right. That's when we would say 88 is not found in the tree. To insert 88, we simply put it in that last spot that it could have been, which was right here. So we can modify our search to be an insert. And, oh, we got 6 minutes. That's like a world of time. All right, let's insert num into the root. You gotta, you know, define these temporary variables to be struct t-node pointers and all that stuff. This is still pseudocode, right? So set your temp equal to the root. And I'm going to assume the num is not in the tree to begin with. So if the root node's data is bigger than temp, let's move to the left. So here our check is if root left equals null, then what should we do? Change root left to be the new node and return. So make some new node up here. So call malloc, get yourself a new T node, set the data equal to num, set left and right equal to null, that kind of stuff. So this is our new node that we want to insert. Start off at the root. If the root node's data is bigger than what you're inserting, you want to move to the left. If there's nothing to the left, change the left child to be equal to this new node and you're done. Otherwise, move to the left, go back up. And down here we do exactly the same thing for moving to the right. Let's see, so depending on order of insert, two trees of identical numbers could be completely different. Absolutely. And that's going to be really critical in a while. So for example, suppose you want a tree with the numbers 10, 20, and 30. Well, here's a tree with that data in it. Here's another binary search tree with that data. Here's another binary search tree with that data. So yeah, the order in which you insert will affect the tree. All right, so this is hopefully somewhat reasonable looking. I want to code this up tomorrow actually and play around with it in the debugger and build some trees. But I want to point out one slightly horrific detail about this. This works great, you know, if you're starting with a binary tree and you're trying to insert something like 88, right? We'll move down when we get here. We'll set the right child of 50 to be our new node. That's all fantastic. There's one case where this doesn't work, which is suppose your original tree looks like that. Suppose you start off with an empty tree. So we start off with a main program. We declare my root to be null to begin with. And if the tree is empty, yeah, we have a root, but the root is null. It's not like a sentinel node. There are no nodes in the tree at all. And if I say insert my root 25 to start off, you know, with a first node of the tree being 25, as soon as I come in here, I'm going to set temp equal to root. Well, if root is null, temp is null. Right here, I'm going to segfault. And here's the challenge. With linked lists, we never had an empty list. If the list had no data, we still had a sentinel. With trees, since we don't have sentinels, if we've got even just one thing in the tree, our root will point to a node. But if there's nothing in the tree, our root points to null. And so we have one special edge case, which is where we're inserting into a node that's equal to null. The problem is, even though what I could do in here is the following. So if the root is null, then set the root equal to the new node. That's great. That's exactly what we want. The problem is, doing this doesn't change the value of my root when I come back to main, because C is always passed by value. I can change the thing that my root points to, the thing, you know, that my root is pointing to, but I can't change where my root points. This is horribly subtle. So what we're going to do is we're always going to return the root of the tree as the function value. So when we call insert, we'll pass it a root, but it'll pass back the root of the tree, and we'll set my root equal to that. And the one reason we do this is that if root starts off null, insert will create a tree with one node. It will come up with a value for the root of that tree, and it'll return it. And this statement right here will set my root to point to that tree. Alright, so don't worry if that's confusing. If it's confusing, it means you were paying attention. We will do some code around this tomorrow. Let's see. Yeah, so this is tricky. When you pass a pointer, you're passing the pointer by value, right? And we cannot change that pointer. We can't change what it points to, you know, where it points. We can change the stuff at the location it's pointing to, but it's always going to point to the same spot before and after the call. And here, my root is pointing to null. What we really want is after insert, we want my root to be pointing to this new node. And we can't do that unless we pass the address of my root and then prototyped it as a star struct t node, and we don't want to do that. So yeah, the root's always just going to start off as null. Yeah, we'll definitely go through this in detail tomorrow. So we'll write some code around this, and we'll see the issues here. All right, so we'll start with that tomorrow, and then let's see. And then we will talk about traversal of a tree, and we'll be working our way towards the fun stuff. All right, cool. Have a good one. I will see you next time.